Okay, everyone, can you see me? Can you hear me? Good evening. Give me a thumbs up. All right, it looks like we're good to go. Congratulations for finishing homework 1. I know you guys worked hard and, we're proud of you. Keep up the good work. And yeah, let's continue our discussion on DFAs, Deterministic Finite Automata. So just a quick review from last time. So we introduced the Deterministic Finite Automata computational model, which is a kind of a restricted model of computation. We saw that we can represent a DFA with a state diagram. You can draw a state diagram to describe a DFA, but we can also actually more formally define it with a 5-tuple. You have all these different components, the states, the alphabet, the transition function, the starting state, and the set of accepting states. And these two representations in some sense are equivalent, right? So all the information that you have in the state diagram is in the 5-tuple representation and vice versa. We then define this notion. The language of a DFA-M is the set of strings that the DFA accepts. And this is the unique language that the DFA solves, right? Or if you think about the corresponding decision problem, it's the unique decision problem that this DFA solves. So because of the equivalence between languages and decision problems, another common word here would be to use like, oh, the DFA-M decides the language or the decision problem corresponding to L. Compute is another word. And then we made the definition of regular language. So any language or any decision problem really that can be solved by a DFA is called a regular language. Great. So now we have this, computational model. The first question that you might ask now is, okay, is every language regular? Or in other words, given a decision problem, or let me phrase it this way, can DFA solve every decision problem out there? Is this like a general enough computational model or not? Our intuition was like, of course not, because DFAs are pretty restrictive. So there should be some problems out there that DFAs cannot solve. And indeed, we were able to reason through, like target the key weaknesses of a DFA and actually show something like 0 to the n, 1 to the n is actually not regular, cannot be solved by a DFA. Another example is like 0 to the 2 to the n. Good. Now, what we're going to be doing in this lecture is, dig a little deeper, prove more properties interesting properties about regular languages. Now that we have this computational model, now that we have this formal definition that allows us to now rigorously reason about this model and, explore new territory, find new properties of this model, and gain new insight, gain new knowledge, right? And this is what we're going to be doing. Okay, so it's kind of like what math is about, right? You have your definition and then you explore all the interesting properties of that definition. So we will be doing that. Now, before I do that though, I want to actually start the lecture with a real world application of DFAs, right? So I think some of you might find this interesting if you care about applications more. Here's an application, a very cool application of DFAs. So here's a very basic computational problem. One of the most basic problems you might say in computer science, it's the string searching problem. So you're given some string S of, let's say, length n. Think of S as a long string, okay? So this is why I'm denoting this with a capital S, like it's a big string. And let's say it has like, I don't know, thousands or millions of characters. And then we have another string W of length K, and we think of K as small. It could be maybe 100 or something like that, okay? And what we want to know, is W a substring of S, right? Does W occur in S or not? So that's the task. This is a very fundamental, one of the most fundamental, tasks in computation, you might say, right? So it's important to really try to find the best possible solution that we can find. Now, one, obvious solution or naive solution for this might be something like this, right? So if I were to ask you, perhaps you might say, well, the obvious thing to do is let's check if W appears starting at index 0 in S. Then if not, let's check if it appears in index 1, is starting at index 2, starting at index 3, and so on, right? So you have this window, and then you sort of shift it one by one. So check it here. No, it's not there. You know, slide it, check it there. Is it there? No. Okay, so you keep going like this, okay? Now, what's the running time? In the worst case, what's going to be the running time of this kind of an algorithm, okay? Well, I mean, every time you are checking a window here, that's going to be roughly k comparisons, right? In the worst case, you have to do like k comparisons to see if W is matching starting at that index. But now how many indices are you going to try? Well, that's about n. I mean, it's n minus k, you might say about, but let's say it's n, right? So roughly the solution here is going to be about n times k steps. I mean, n minus k times k steps, but about n times k steps, right? Good. So this is actually exactly what you guys are telling me in the chat right now as well. Very good. Now that you might be okay with that, but as I said, this is such a fundamental problem. Like, you want to do better if you can do better. And a good algorithm designer always asks, can we do better? And usually the answer is yes, you can do better. So you should try to find a better solution. Okay, so then how can we do this better? So here's a DFA solution to this. So if you notice, the task here, really, when we want to know whether W is in the string S or not, is to check whether this string S is in this language. I'll call it L sub W, which is the concatenation of sigma star W sigma star. Okay, so if you look at this language here, if you take a moment to think about it, this is the set of all those strings that contain W as a substring. Okay, so sigma star concatenated W with concatenated sigma star is a set of all strings that have W as a substring. So if you believe that, then our task is really to figure out, is S, capital S, one of those strings, right? Is S as is an element of LW, L sub W or not? Good, so that's great. Now it turns out, of course, like you can think about this, here's an exercise for you. L sub W, for any W, is a regular language, right? It's not that hard to see, actually. If you think a little bit about this, I think you can convince yourself this is indeed true. And since it's regular, we know that there's going to be a DFA. Let's call it M sub W, computing, deciding L sub W, right? Now, once I have this DFA, what am I going to do? I need to check if S is in this language or not. So I'm just going to feed it into the DFA, right? And now what is the running time of that going to be? How many steps does it take, to run that, to get the answer? That's going to be n, right? Like, I mean, this is like one of the key things about DFAs, right? Once you have an DFA algorithm that solves a problem, that solution is blazingly fast, right? It's pretty much as fast as you can hope for, because what does a DFA do? It scans the input exactly once. It will read every symbol just once. When it reads a symbol, it's not like it's doing anything complicated, right? It's very simple. It's just changing a state, basically not doing anything. And at the end of that, it's going to make a decision, right? And in most problems, you have to read the whole input anyway. So it's like as good as it gets, right? In some sense, in terms of algorithm. And one of the things I said when I introduced the DFA model, like, why would you want to, study a restricted model of computation? Well, this is one of the reasons, because, with the DFA model, we know like that restriction actually is in some sense one of the good things about the DFA, is an advantage of the DFA. It allows us to come up with super fast algorithms that we know are going to be linear time, right? And you know that if you have a DFA solution, that solution is, doesn't have like infinite loop bugs or anything. It's always going to run in linear time. So that's great. Now, this takes, as we said, about n steps. Now, there's one more thing you need to do, of course, which is you have to construct M sub W. So you have to take that into account in your analysis. Time to build MW, well, you can think about it, and there's a simple algorithm that takes roughly k cubed steps. And what you can do better, in 1977, Knuth, Morris, Pratt did this in k steps. So now we have an algorithm for this problem that is roughly n plus k steps compared to the naive solution, which was n times k steps, which is much, much better. By the way, this is a major result in computer science. James Morris is a Pittsburgh native, was a CMU undergrad, just like you, became a CMU professor, was dean of SCS at some point, now retired. But anyway, if you see him, give him a high five. Okay, this is a major result in CS. So DFAs are actually quite useful in these kinds of like string searching, pattern matching kind of algorithms. And I'll say more about that later in the lecture. But here's one concrete application of DFAs. All right, so now I want to talk about other interesting properties of regular languages. I want to prove to you some interesting properties. These are going to be closure properties of regular languages, and we're going to do three results, three theorems, if you will. First one is going to be pretty straightforward, like one slide should be enough for it. It's going to be okay. The second one is going to be medium spicy. Okay, it's going to take some thought to reason through it and understand it and motivate it. And then we're going to do a third one, which is going to be somewhat spicy, on the spicy end of things. So we're going to be increasing our level of sophistication, as we progress through this lecture. Okay, but hopefully the main ideas I'm hoping will be clear. Okay, so what do I mean by closure properties of regular languages? What do I mean when I say something like regular languages are closed under complementation operation? Here's what I mean. All I mean is that if L is a regular language, then so is the complement. Okay, the complement of the language is basically sigma star minus L. So this backslash notation denotes the set minus notation. So if L is regular, then I'm saying complement of L is regular, and that's what it means to be closed under, complementation. Regular languages are closed under complementation. Good. Now, when we do these proofs, this proof, the next proof, and so on, I don't want to just like present to you the proof and say, look, here's the proof, this is how it goes, and then be done with it. I want to actually motivate, I want to tell you how would you think about these kinds of things? How would you approach it? What kind of ideas can you come up with? And then at the end, how do you write these kinds of proofs? Right? So I want to take those steps carefully. Now for this one, I won't have much to say because this is relatively simple. But nevertheless, the first thing I would do when I see a statement like this that I need to prove, the first thing is for me, let me lay out explicitly what are the assumptions that are given to me, what can I work with, and what is the statement that I need to derive, okay? And then I will unpack the definitions if appropriate, okay? So in this particular case, what am I given? I'm given a regular language L. Unpack the definition, what does that mean? It means that there's a DFA, let's call it M, that solves the language L, okay? Good, so that's what I'm given. What do I need to derive? Well, I need to show that the complement of L is regular. Unpack the definition. What does that mean? It means that I need to show that there exists some DFA, call it M prime, that solves L complement. Okay? Once you do this, this could be, for many proofs you write, this could be just the first paragraph of your proof, right? You neatly write down what is given to you and what you need to do. And that actually gives you a nice, big picture view of what has to happen, where do you start and where do you have to go, okay? So the first sentence of your proof is okay, let's just write it down. This is what's given to us. If L is regular, then there's a DFA. Write down the 5 components. And that solves your language L. Now, what do you think the overall proof strategy is going to be here? Do you think this is going to be a proof by contradiction? Is it going to be proof by induction? Is it going to be something else? What kind of strategy? Yeah, so this is what we would call a direct proof, like a direct constructive proof, right? Why not? Because like, it seems like it doesn't make any sense to go by contradiction or anything. What you're going to do is here, you're going to construct the DFA M prime directly. And of course, you're going to be making use of the DFA M, right? So then how can I, whoops, I didn't want to give it away, sorry. So how can I actually construct this M prime? Right? I mean, we kind of saw an example from last lecture, right? So we had this language with two strings. I don't exactly remember what the strings were, but I think it was like maybe 110 and 101. We drew a DFA for that. And then we looked at the complement of that language. And what we said was, oh, we can just like swap the accepting and rejecting states. And then when you swap the accepting and the rejecting states of M, what does that mean in terms of the 5 tuple? You guys have it already, in the chat. All that means in terms of the 5 tuple is that everything stays the same except that the set of accepting states now is Q minus F, right? So that's exactly operation of swapping accepting and rejecting states. And then you might say, okay, so then so this machine recognizes solves this L complement and put a box. Now, one question to you. Can I put a box here, or do I need to argue, do I need to prove that actually M prime indeed solves L complement? So what do you guys think? Does that require an argument here or not? Some saying probably need to. It's not 10,000% obvious. Most certainly, likely, yes. Okay, interesting. I would say my personal preference here is no. I think you're pretty much done. I think that it is pretty clear that this, will solve L complement. You can give the proof, right? I mean, I wouldn't object if you wrote the proof. I wouldn't say, well, that's like too much detail. I think maybe it's borderline case, but in my opinion, for my taste, I would say this is enough. Especially if you say, I think, in your proof, if you say like the idea is to swap the accepting and rejecting states, and to accomplish that swapping, what you need to do is, define your set of accepting states to be Q minus F. If you say that, I think you're pretty much done. Okay. If you don't say that, oh, I'm swapping, maybe then you want to say a bit more. But yeah. So that's my opinion on this one. Let's go to the next one. So now this is medium spicy. Regular languages are closed under the union operation. What do I mean by this? What I mean is that if you have two languages, L1 and L2, that are both regular, then their union, L1 union L2, is also going to be regular. Okay. Now, once again, I'm going to do the same thing. What is given to me and what do I need to derive? What's given to me is two regular languages. So I know that there's a DFA M that solves L1. There's a DFA L2, M prime that solves L2. And then the goal is to construct a DFA, let's call it M double prime, to solve L1 union L2. So you can write this out, right? So this is like the first paragraph of your proof. At this point, you have no idea perhaps how to figure this out. You don't know how the proof is going to go, but at least you know how it starts, and this is how it's going to start. And once again, I think it's very reasonable to expect that this is going to be a proof by construction, like a direct proof, just like we did before. And of course, M double prime, the construction of the M double prime, will depend somehow on the DFA's M and M prime. Okay, good. So now this is the task at hand. Okay, so now what do you do though, right? I mean, how do you construct this DFA M double prime? It's not immediately clear at all, right? In the previous case, I think we had, more clear vision of what to do. But here, it's not as clear. So then we have to really reason through this slowly. Okay, now how can we do that? Well, recall a DFA is what? A DFA, as I said in the last lecture, is a very restricted programming language in some sense, right? You can think of it that way. And if you think about like a programming task. Maybe you're taking some intro programming course, you're learning how to like write Python code, and in the homework you're given some problem and you need to solve some task in Python. Like as a teacher, what I would recommend to you is I would say, look, forget about Python, forget about the syntax, and think about how you yourself would solve this problem. Okay? Imagine you have some long input. What would you do to determine what the solution to the problem should be? Now, once you do that, if you can do that, then you've done the hard part in some sense. You've done the creative part, and all that remains will be to take what you did and transfer it into Python code. Now, that step can be a bit difficult if you're not used to the Python syntax, but if you are used to Python syntax, then that step actually is the much easier part of the process. Now, given that DFAs are just some restricted programming language, you can do the same thing, right? I'm gonna recommend to you that in situations like this, imagine yourself as a DFA and ask, how would you yourself solve this? Okay, so here's the mindset that we want to follow. Step 1, imagine yourself as a DFA. Now, since DFAs are like a limiting computational model, of course you want to apply the same restrictions to yourself as you're thinking about yourself as a DFA, right? So what are those restrictions? What are the rules that you need to follow? For one, you have to scan the input only once from left to right. Okay, so you have to follow that rule. And 2, you can only remember constant amount of information, right? So you only have constant number of states, and the only way to remember stuff is really through the states. So that kind of means basically that you have constant amount of information, where constant means cannot change based on the input length, right? So no matter what input length you have, whether it's like 10 symbols long or 100 or 1,000,000 or 1,000,000,000, the DFA only has a constant number of states, a fixed number of states, and that's all it can use. Okay, so that's what it means to have constant amount of states, constant amount of information to work with. Good. Okay, so we're going to apply these restrictions to ourselves and try to come up with a solution. But then once you do this, I would claim that most of the time you're 80%, 90% done, right? Because the next step is going to be basically now define yourself as a DFA, right? Write down yourself as the 5 tuple of the DFA. What's your set of states? What's your transition function? What's your starting state? And what is your set of accepting states? That part is not really the creative part. The creative part is step 1. So, and step 2 is really like, putting down everything using mathematical notation. Now, that can be difficult and that can be challenging at first, okay? So if you're not used to mathematical notation, and if you're not used to that process of going from like ideas down to mathematical notation, you might find that challenging, and that's completely fine, right? Don't feel bad at all if you find that challenging. But nevertheless, you should know that, that is not the creative part. That's just a matter of getting used to, okay? So you just have to spend the time, get used to it. And once you're used to that, then you'll see that, it's relatively straightforward. So really step 1 is the important part. Good, so now let's do this, right? We're going to come back to our, union example that we are trying to do. So we're going to imagine ourselves as the DFA. Now, how can we do this? Well, another, tip that we recommend, another thing that we recommend when you're trying to solve a problem is to work with small examples to build up your intuition, okay? And this is exactly what I want to do with this one. I want to actually define some languages, L1 and L2, just some small examples, basic examples that I can work with, and see then if I can find a construction for their union. Okay, so my first language is going to be L1, strings with even number of ones, and L2 is going to be strings with length divisible by 3. Okay, now let me actually draw the DFAs for these ones. Okay, so this is the DFA for L1. And here's a DFA for L2, this M prime. Okay. Good. So we have these DFAs, and now I'm going to ask you, right, like what is our task first of all here, right? So we want to construct a machine that decides the L1 union L2. So we're imagining ourselves as like, you know, the DFA. So our task really is given a word, given a string W, we want to know, is it in L1 or is it in L2? If it's in one of them, then we should accept. And to now figure out whether it's in L1, L2, given that we have these DFAs, what would you do? Well, you know, a natural thing to do would be to, I'll run it in the machine M and see where it goes. I'll run it in the machine M prime, see where it ends up. And if one of them accepts, then I want to accept, right? Now, what's the problem with that? What's the problem with, you know, the strategy that I just described? Yeah, I can, right? I have to now remember that, look, I have some restrictions that I have to respect. One restriction is that I can only scan the input once. And the way that I just described to you, it would require 2 scans, because I would have to like first feed it through M. So that will be 1 scan. And then I go back and feed it through M prime. That will be the 2nd scan. So I can't do that. Okay. So then what should I do instead? What can I do to fix this? Yeah, I'm saying, can we merge DFAs, duplicate the digits, read them simultaneously? Yeah, so that's a nice idea, right? If I could, so what I would like to do, I have the input, I'm going to scan it once, and if I could now somehow simulate both machines at the same time, right, then that would work, right? So why not try that, right? As we're scanning, let's try to simulate both machines at the same time. You know, in programming lingo, you would say like open up 2 threads, 2 separate threads, and run them together. So let's see how that would go, okay? So here's a sample input, 101, 001. I have 2 threads. One thread, this is thread 1, is going to keep track of the first machine M. The second thread is going to keep track of the second machine M prime. And then we'll advance both machines at the same time. So initially we start at the starting initial states of both machines, right? That's P0 and Q even. Now here in my table, I'm denoting Q even by QE because I don't have quite enough space here to write it all. So QE denotes Q even. And then when I read the first symbol, right, that takes me to Q odd. So here I have Q sub O. So again, this is a shorthand for Q odd. So every time in the first thread, every time I read a 1, I go to the other state. I switch states. In thread 2, every time I read a new symbol, doesn't matter whether it's 0 or 1, I will go to the next state. Okay, so that's after one step. So after reading another 0, then I'm going to stay at Q0 here, and then I'm going to be at P2. After another 1, then I'm at QE and P0. Another 0, QE and P1. Another 0, QE, P2. And then finally QO and P0, right? And then I'm done with the input. Now, what's this decision going to be? Right, so I'm going to be checking here among Q sub O and P0, is one of them accepting, right? So in this case, we see that P0 is accepting. And since one of them accepts, the decision should be to accept, right? So in general, if at least one of them accepts, then we accept. If both of them reject, then we would reject. Very good. Now I have to ask, okay, I did this process. Did I respect the conditions, the restrictions of a DFA as I was doing this, right? So the first question is, are we scanning the input only once? Or did I scan it more than once? No. I mean, I did indeed scan it only once. So that's good. So that we respected. Second question is, do we need to remember more than a constant amount of information? Well, what are we remembering at each unit, at each symbol? Well, we are remembering one state from the first machine and another state from the second machine, right? Two states. And now the question is that a constant amount of information, or is that something that needs to grow as the input grows? What do you guys think? Right? It's constant, right? It doesn't matter if the number of symbols I had here was 6, but it doesn't matter if I had 6 symbols, 100 symbols, a million, a billion symbols. No matter what, I'll only need to remember one state from the first machine, another state from the second machine. And that's constant. That does not grow with respect to input length. So now at this point, I feel great, right? Because now I feel like I'm basically done with step 1. I've convinced myself that this can be done using one scan through the input and only remembering constant amount of information. So I know that there's a DFA for this. Now the second step will be to actually write this down formally and define myself here as a DFA. And we'll do that. But before we even go there, let me spell this out even a little bit more. Let me even draw out the DFA for this particular example for you. Let me draw out M double prime and what it would, and so you can see what it would look like before we even define the DFA formally. Okay. So the main idea here is construct a single DFA, which is going to be M double prime, that keeps track of both M and M prime. And now, how many states is M double prime going to have? We're going to have 6 states, right? Why? Because it corresponds to, every state corresponds to a tuple of states. The first coordinate comes from the first machine, the second coordinate comes from the second machine. The first machine has 2 states, the second machine has 3 states, so in total we get these 6 states. Good. What is the initial state here? Which one should I label as the initial state? Right, Q even P0, you got it. Why? Because Q even is the initial state of the first machine and P0 is the initial state of the second machine. Which ones should be the set of, which ones should be accepting states? How can I determine the accepting states? Yeah, correct. So if one of the coordinates is an accepting state of the corresponding machine, then I should be actually accepting. So in this case, what does that mean? We know that Q even is an accepting state of the first machine, and we know P0 is an accepting state of the second machine. So that's why if the first coordinate is Q even, we are accepting, and if the second coordinate in addition, if the second coordinate is P0, then we accept. Good. Now, what about the transition function? So if I were to, for example, look at the initial state and I want to know where will the 0 transition go from the initial state, how do I determine that? What would I do? Well, what I would do is I would, advance the first coordinate, Q even, according to the transition function of the first machine, and advance the second coordinate according to the transition function of the second machine. Right? So we know that 0 actually does not change the state of the first machine, so that will keep Q even. But no matter what we read in the second machine, we go to the next state, so P0 should become P1. So that's why this goes to Q even P1. And if it was a 1, then in this case, Q even would become Q odd, and P0 again would be P1. So we would go there. As another quick example, if we were in Q odd P1, well, the 0 doesn't change the first machine, so that's going to stay Q odd, but P1 will become P2. So that goes there. And then if it was a 1, then we know Q odd is going to become Q even, and P1 is going to become P2. So that goes there. Okay, and you call like this, and then voila, you have all your transitions, and here's the full complete DFA picture for you. Now, this kind of looks complicated. I mean, lots of arrows flying around, but hopefully you agree that the idea behind the construction is relatively simple. And and then you can simulate this machine now, but this is basically the DFA for the particular example L1, L2 that we had, and M and M prime we had. And now, we feel great about this, and all we need to do is now define formally m double prime. Okay, so let's write this out, formally defining the union construction. So we will be like, okay, let M be the DFA, let be a DFA solving L1, let M prime be a DFA solving L2, and then now we construct M double prime solving L1 union L2. And then we specify now each component here. So what's going to be Q double prime? So who can tell me how we're going to define Q double prime? Of course, we're going to be making use of M and M prime here to define the components of M double prime. Right, exactly. I mean, we have a tuple, as we said. First coordinate comes from the Q, capital Q, and the second coordinate comes from Q prime. Right, so we can write this, the set of all tuples where the first coordinate comes from Q and the second coordinate comes from Q prime. That can be written using the this notation here, as you can see, Q times Q prime. But you can also write it in this following way using set builder notation. It's all those tuples Q comma Q prime, such that Q is in capital Q and Q prime is in capital Q prime. Good. Now the alphabet is the same, so we don't have to define that. That's the same sigma. Now we go to the transition function delta double prime. Now the signature of the transition function is, just like we've seen it before. The transition function is always, of the form Q times sigma to Q, but in this case our Q is Q double prime times the alphabet, and map is set to another state Q double prime. But we know Q double prime is Q times Q prime, so I could also write this if I wanted in this manner. It's the same equivalent way. Now, when I want to define a function for you, how do I define it? Right? How can I define a function? What's the way to specify what the function is going to be? We have to do what? Yes, so you have to basically, for each input, you have to tell me what the corresponding output should be. Once you do that, you define the function. And a way to do that would be to say, okay, let's consider some arbitrary input. So take some Q, small q in the capital Q, some Q prime in capital Q prime, and some symbol, small sigma. So this is like in Greek, this is small, this is capital sigma, this is small k sigma. Some sigma in capital sigma. Okay, so these are all in some sense arbitrary variables now, denoting arbitrary elements of these sets. And then now define for me what the function should be, right? So what it should be delta double prime, right? Now this is Q prime, this is the state, and then the symbol. Right. Very good, right? So I'm seeing the right answers here. Probably I need to go smaller here. Right, so what you do, the idea is basically you advance the first coordinate according to the transition function of the first machine, and you advance the second coordinate according to the transition function of the second machine. So if you put that in notation, that means you apply the first transition function delta to Q and sigma, and then the second coordinate, you apply the transition function of the second machine, delta prime, to Q prime and sigma. Okay, and then this is your new state, the tuple that you have. Good. And then we're almost there, right? So then we're going to have Q0 double prime. What is this going to be? We already seen it in the previous example. The initial state is just going to be consisting of the initial state of the first machine and the initial state of the second machine. So that's Q0 and Q0 prime. And how about the set of final accepting states, F double prime? Yeah, so F Q prime, F times Q prime union Q times F prime, F prime union F union F prime I'm seeing. So that's actually not gonna work, right? So why does not, so F So I'm seeing, like, for example, F union F prime. Does this type check? Right, so you have to remember that, oh, the set of states of the new machine is consists of tuples, right? So this is not a set of tuples, so that doesn't work. And F, this will also not quite work, right? So I think you guys are making it a bit more difficult, maybe trying to get like a concise Cartesian product representation here. I think it's much clearer to use just a set builder notation. And when I write it in set builder notation, I think you're going to see that it's clear that it's correct. So it's the set of all those tuples, right? Q comma Q prime, where either Q is an accepting state of the first machine or Q prime is an accepting state of the second machine, right? So I hope that, you know, in this notation, it's pretty clear. You can write it in terms of Cartesian product as well and the union. That's fine. But I find that this is actually clearer. When you read this, I think you're like, yeah, of course, that's the set of accepting states. Okay. Now you've defined the DFA M double prime, and now you might be like, okay, what do I need to do? Well, maybe it remains to show that this is indeed a correct DFA that actually solves the L1 union L2. So you might go about this by proving a double containment, doing a double containment argument, and finish the proof like that. Now here's another question. I mean, we had this question in the previous one, and I'll ask again, actually. Is this part necessary for the proof? Or can we just say, look, here is the DFA M double prime, and we're done? Depends on the audience. Very good. I totally agree with that. Necessary, not obvious. Correct. Yeah. So here is my answer to this. It depends. It depends on what you have done before, basically. Okay. So if this is your proof, right? So you start by like, oh, let M be the DFA for L, let M prime be the DFA L prime, and here's the 5-tuple representation of M double prime, and then bam, that's it. Then I would say no, that's not okay, right? Because you didn't explain anything, you just like constructed something and you're just claiming that this works. If on the other hand, so in that case, I should say, in that case, you have to write down these arguments right here at the end. If on the other hand, you had like a very nice explanation, like just the way maybe, we did, we reasoned through it and we said, look, the idea here is to really have two threads and run these machines simultaneously. And then the way to do that would be to like have a tuple of states, one for the first machine, the second is the second machine. And then you advance the first coordinate according to the first transition function and so on and so forth. So you give all that explanation, then I think, you do that and then you give this construction, then that's pretty convincing in my opinion, right? So if I read that, I'm going to be like, yeah, that makes total sense. You got it, right? But as I said, if you don't do any of that explanation and you're like directly, oh, here's the 5-tuple definition of M double prime, that's not enough. Okay. Good. Now that we have this, we can also easily see from this that regular languages are closed under the intersection operation, right? So what would be a way to see this? Oh, yeah, so there is a typo. So this is supposed to be intersection. Thanks. Okay, so what can we use? Right, so I'm seeing basically De Morgan's law, right? So we can do that. Follows from these following three facts. We can say, look, L1 intersection L2 is nothing but L1 complement, union L2 complement, and then complement the whole thing. We know regular languages are closed under complementation. We know regular languages are closed under union. So then that's it, right? Basically, then the L1 intersection L2 is going to be regular because L1 is regular, so the complement of L1 is regular. L2 is regular, so the complement of L2 is regular. So then L1 complement union L2 complement is regular, and then the complement of that whole thing is regular. So all these operations, the union and complementation, they preserve regularity. So from that, we get that L1 intersection L2 is regular. By the way, you can also do this, you can see this from the previous argument. You can take the previous argument exactly as it is, and then change one word in it. So you take that or, and you make it an and. Okay, and then that's also a correct way to see that regular languages are closed under intersection. Great. Cool. Okay, so let's do closed under concatenation. I think this is a fascinating proof, fascinating construction. Now it's a bit spicy, right? So focus on the big ideas here, even if you don't follow all the details, that's fine, but I hope that you will get the main idea and what's going on here. Okay, so this is what we need to do. We have two regular languages, L1, L2, and we want to show the concatenation L1, L2 is regular. Recall the concatenation of two languages is what L1, L2 is, just the set of all those words U, V, such that U is in L1 and V is in L2. Or in other words, we can say basically, look, a word W is going to be in the language L1 concat L2 if and only if there's an index I such that, you know, the first part of the word W1 to WI is in L1, and then the second part WI plus 1 to WN, let's assume W has length N, and then that part is in L2. Okay, so that's the task really. Like given a word W, we need to know, can we break it up somehow in the middle such that the first part is in L1 and the second part is in L2. Okay, and the strategy is going to be the same as what we did with the union construction. You know, imagine yourself as a DFA. Can we figure out if we can break up W into two parts such that the first part is in L1 and the second part is in L2 by scanning the input only once from left to right and only remembering constant amount of information while we do that. Okay, so that's the task. And then once you can do that, you're 90% done. The second step is just to formally define the DFA. Okay, so let's imagine ourselves as a DFA. And again, I'm going to sort of think of this as using an example, right? So I have one language, L1, maybe the DFA for it looks like this, M. And another language, L2, maybe the DFA is M prime, looks something like this. And as we said, like what we need to do, our goal here is to determine, given a string W, can we write it, can we break it up as UV, such that, you know, M accepts the first part U and M prime accepts the second part V. Okay? And yeah, but the issue, so what's the problem though? Okay, so that sounds good. The problem is with this is that what makes this tricky is that we don't know where U ends and V begins. We don't know how to break up W as U and V. If we knew that, maybe okay, we can do this, but if we don't know that, what can we do, right? So when do you, we can start feeding W into the first machine M, but when do you stop simulating M and start simulating M prime? That's a problem. So now how can we fix this? But I mean, we have to work with this. This is what we need to do. So let's make some simplifying assumption. Suppose like you have a good relationship with God, okay? And God tells you, look, U ends at W3. So that's the breaking up point, right? W1 to W3, that's one part, and then the rest is the other part. Now, if God tells you that, hopefully, then you can say like, okay, I can work with that and I can figure this out, right? So you can maybe simulate, you can consider like an example input like this, W1 to W10, an input with 10 symbols, you know, all these bits. What you're going to do is you're going to simulate the first machine. Start simulating the first machine, right? You know, you start at Q0 of the first machine, you read W1, okay? You go to Q1. You read W2, that keeps you in Q1. You read W3, that takes you Q3. And now it better be the case that Q3 is an accepting state, right? Because here W1 to W3 should be in L1, which means that M should accept it. And indeed, that is the case. Good. So you're happy with that. And then now at this point, you're going to start simulating the second machine now, right? So you're going to say, okay, I'm going to start Q0 prime now. The second machine states are labeled with primes. So this is Q0 prime. Now I read W4, it's Q2 prime. And then you keep going like this. Now at the end, I am at Q1 prime, right? And then I check, is Q1 prime accepting in the second machine? If it is, then I'm like, okay, good, that works. And indeed, Q1 prime is accepting. So this does work. So God was telling the truth in this case, and we could check that. Okay, but yeah, so the thing is, like, I'm not a religious man, right? You know, we cannot rely on God, right? We have to figure this out by ourselves. But nevertheless, you know, this is an interesting concept. So let me give a name for this, first of all, okay? So a simulation of M and then M prime that corresponds to breaking up the input W into UV, where U is in L1. I'm going to call this a thread. It's like a concatenation thread, basically, okay? So this whole thing, basically, right, what I have here is a concatenation thread, or simply I'll call it a thread, okay? I want it to correspond to breaking up W into UV, right, such that U is in L1, meaning that this should be an accepting state. But I don't insist that Q1 prime is accepting, right? Q1 prime, like the end one here, it could be accepting of the second machine or it may not. But what I can say now with that definition in hand, what I can say is that I know that W is in L1 concat L2, if and only if there exists a concatenation thread that I just described, like here, ending in an accepting state of the second machine. Okay? So hopefully everyone agrees with this, right? So this is like an interesting observation, right? So we're building up our intuition here. And what this suggests is, right, so if I want to determine if W is in the concatenation L1, L2, then what I should try to do, what I would hope to be able to do, is to check all possible threads and see if one of them ends in an accepting state of M prime, right? That's what I would like to do, to try all possible threads. Now that seems like it should not be possible with constant amount of information, but nevertheless, let me roll with this idea, okay? And then we'll see, we'll analyze if it works or not. If it doesn't work, maybe we can fix it, maybe not, we don't know yet, but I mean, we should just explore this idea nevertheless. So let's try to run all the threads simultaneously and see what happens. Okay, so here's an input. Now let me make myself smaller here. Good. Okay, so I have an input with 11 symbols, and I'm going to start simulating the first machine. So we start with Q0, then we read the first symbol, that takes us to Q1. We read the second symbol, W2, that takes us to Q1. Reading W3, now we're at Q3. Now, Q3 is an accepting state, which means that this is a possible breaking up point, right? So then I should start a thread here, the concatenation thread. So you can imagine we're going to be automatically teleporting from Q3 to Q0 prime here and open that thread up. Right now we have Q0 prime. And now I'm going to keep, simulating both machines, right? Because I need to keep simulating the first machine because I might have to open up new threads, right? So whenever I reach an accepting state of the first machine, I will need to open up a new thread and see if that works or not. Okay, so now let's keep them going then, right? So we keep simulating the first machine, that's Q2. Now this is Q2 prime. Then after reading W5, we are at Q4 in the first machine. which means this is another breaking up point, right? So it could be the case that U is W1 to W5 and V is W6 to W11. So I need to check for that. So I open up a new thread. Okay. So now thread 2, since I've reached an accepting state here, I start a new thread Q0 prime. Okay, now we advance all of them, right? We keep going. Q1, Q2 prime, Q1 prime, and so on. And then after reading W7, again, another accepting state, which means I need to consider the possibility that like my U is going to be W1 to W7, that will be the breakup point, and then W8 to W11 will be V. So given that, I open up a new thread to account for that possibility. So now I have a Q0 prime here, and we're going to advance. So we keep going like this. And then here, W10, another thread opens up, thread 4, and then we're done. Now, should I be accepting or rejecting based on this information? All right, what do I need to do? I need to look at all these prime, these guys, right? And I have to check, is one of them an accepting state? Is it? Is one of them accepting? Yes, Q2 prime. And actually that's interesting because you see it wasn't going to work until thread 4. Those thread 4 saved us. So Q2 prime works, which means like when did we open up that thread? This was like when we read W10. This was an accepting state, and then we opened up that thread. So the partitioning that works is W1 to W10 is your U, and W11 is your V, and that partition works, corresponds to thread 4, and then Q2 prime, that's an accepting state, and it works. Good. But now, one thing is with respect to the restrictions that we have, absolutely, like we have scanned the input once, right? So in that sense, we're great, right? I didn't scan the input more than once. I never went back and did a scan again. We just scanned it once, so that's good. Now, the other question is, when we look at what we need to remember, is that constant amount of information? No, right? Because what am I remembering here? Right, I am remembering a sequence of states from the second machine. Right, so here you can see Q2 prime, Q1 prime, Q1 prime. And that sequence can grow, right? So it's possible that every time I read a symbol, I open up a new thread, let's say. So every time I read a new symbol, new thread, new thread, new thread. So then you can see like, oh, like I'm creating new rows here, all right? So then if I have, let's say, n symbols, it's possible that I have like n threads. And then I need to remember like, potentially like up to like n or n minus 1 states from the second machine, right? A sequence of n minus 1 states. So that is not constant anymore. Like that does grow, potentially grows with the input length, right? So that seems to be a problem. But is it a problem? Or can we fix it? So how can we fix that? Yeah, I think I'm seeing the right ideas. Like, yeah, exactly. There seems to be a waste here, right? So for example, look at here, Q0 prime, Q0 prime, right? So this is duplicated. So when you look at that column, Q0 prime is duplicated. And of course, when you have this, well, the way you're advancing here, it's the same, right? It's exactly the same. Of course, it's going to be the same. This is a deterministic automaton. So you're going to end up in the same place. So then why did we need that second copy? It was completely irrelevant, actually. We don't need that second copy. We don't need to keep track of that second copy. Or look at, for example, here, like we have Q2 prime and we have Q2 prime, right? So then, these are the same, right? So it seems like we don't need to keep track of duplicates. Like when I'm looking at a certain column here, there's no need to keep track of duplicated states. It's not gonna change my decision at the end. So I can actually do a simplification, right? I can basically collapse these things, right? I can just ignore the duplications. Okay, so that's the main idea now here. So then let me put this up now. So then so let's now ask, what do we need to remember at each point? Well, I certainly need to remember like a state from the first machine. That's fine. That's one state from the first machine. And then I need to remember like these rectangles correspond to states of the second machine. I said, well, you know, it was a sequence, but now we're saying we don't care about duplicates. Then what can I say about what kind of a structure I can use to represent this? If I don't care about duplicates, yeah, a set structure doesn't care about duplicates, right? So these are all actually not sequences of states from Q prime, but they are subsets of Q prime. Duplications don't matter. And now I can say, well, at any point, I need to remember an element of Q, so that's okay, and a subset of Q prime. Now, is this constant amount of information? Well, you know, a subset of Q prime is an element of the power set of Q prime, right? That's like a mathematical way to say this. A subset of Q prime, yes, it's like a bigger thing, but you know, it doesn't grow. A subset of like the power set of Q prime does not grow with input length. Whether I have 10 symbols in the input or 1,000,000 symbols in the input, this doesn't grow. It's still a power set of Q prime. And so this is actually indeed constant amount of information. So actually I'm very happy. And once you do this, you're like, okay, you've done the creative part. You've convinced yourself that you can do this with one scan of the input and by remembering constant amount of information. And so there should be a DFA for this. I mean, there is a DFA for this. And now the trick is to take this idea and define your DFA formally. Okay. And now this can get tricky if you're not used to the mathematical notation. For example, if you're not used to thinking about power sets, if you're not used to thinking about Cartesian products, then okay, you know, definitely, you know, that might be challenging for you. But on the other hand, this is just a matter, as I said, it's a matter of getting used to. Okay, it's just notation, really. So it's like learning a new language like French, if you will. Okay, so great exercise for you now. So you have the DFA for the first machine, for the first language, you have a DFA for the second language, and now you want to define the components of the concatenation construction. Okay, and I'll give you 2 pieces of this to get you started, but I really would like you to do this exercise for yourself. Like, I mean, of course, I can tell you what these are, but it's much more valuable if you actually sit down and figure it out yourself. And I hope you'll do that. So I'll tell you Q double prime. Actually, you tell me Q double prime. What's going to be Q double prime? So we need to remember a state from the first machine and a subset of states of the second machine. So as you guys write down, right, this is going to be Q times the power set of Q prime. And yeah, so this actually, let me write this, like, you know, just to say, like, this is just like Q S, where Q is from the first machine and S is just a subset of Q prime. Okay, so this is another way to write it. Maybe that, you know, this set builder notation you might find more intuitive. How about F double prime? Let's figure that out too. What should F double prime be? In set builder notation, right? So we have Q comma S. Q is a state from the first machine. S is a subset of states from the second machine, right? So Q is in Q. S is in the power set of Q prime. And when do I accept? I accept if, yeah, so if the intersection of S and F prime is not empty, right? So if there is a accepting state of the second machine in S, then that's good, then we should be accepting, right? That's what that means. Okay, so I'm gonna leave it at that, and I would like to really, for you to think about this. Now, look, this is a hard example, complicated construction. Focus, first of all, the main ideas. Actually, I would say, first of all, really try to understand the union construction and understand that well before you jump into the concatenation, because this is a much more advanced version of that. Make sure that you understand the union construction really well. Once you're comfortable with the union construction, then come to this one, okay? First, understand the main ideas behind it before you go to this stage of like really formalizing in terms of the 5-tuple. And then once you're comfortable with the main idea, then see if you can write it out, transfer it into mathematical notation. A very good exercise. Okay? All right, so that's it for me for this week. Next week, we're going to be doing Turing machines. It's going to be fun. But yeah, for now, I'll leave you with this. I'll hang out actually in Gathertown right after this. Once I, close my setup here in 5-10 minutes, I'll be in Gathertown. So if you have questions, if you're confused about something, come and ask. If you want to go through the construction explicitly, the 5-tuple, we can do that together. Okay? So see you guys.